Okay, so we have seen that there is a nice duality between time and frequency domain. We can move our viewpoints from the time domain to the frequency domain. Uh, and in that process, in case if you are considering convolution operation going on, for example, in time domain, then when we move our viewpoint to frequency domain, it kind of nicely simplifies to just a regular product operation. Now, let us change our track a little bit and start doing some examples of Fourier transforms. Now, maybe at least temporarily, we will kind of take our attention away from the convolution and then focus fully on understanding this Fourier transform in itself. And so the best way to start this exercise is to begin by considering some very simple cases. So that is what we will be doing now. Uh, okay, so let us consider one very simple example of the Fourier transformation where uh, we are letting the signal to be just a complex exponential phasor rotating at a certain frequency that I'm calling it f of c. This f of c is a terminology that is widely used. C here represents the carrier. So what this means is that it's a complex exponential phasor rotating at a carrier frequency f of c. Why carrier, where that terminology came from, we will get to that later on in the subsequent slides. But let us just do the Fourier transformation of this x of t. This is the Fourier transform formula here. Remember, this minus sign is coming because of that conjugate operation. And in this formula, if I plug x of t, I get the second line. And I simplify the integrand and I get this expression over here. Uh, and then when I consider this entire integration, I am left with just a delta function uh, at f of c. So where is this coming from? Why is this integral equal to this delta function? That we have seen earlier. If you go back to probably the first lecture or the second lecture, on slide number 8, when we defined the direct delta function, if you recall, uh, this is the equation that we had seen for direct delta. And according to this equation, when uh, we are integrating over some variable y, this integral going from minus infinity to infinity evaluates to delta of x. And so that equation 2, is what we have used in this particular example. Variable y of that equation is now variable t, and x is f minus fc. And so this is the same as equation 2, and therefore this becomes delta of f minus fc. What is delta of f minus fc? Again, we go back to our previous slide, maybe slide number 9 or something, where we had concluded that if I have any function f of x, then f of x minus x0 is f of x shifted to the right by x naught. And so in case of f of x, if I have delta of x, or rather delta of f, then delta of f minus fc is nothing but the original direct delta function, which is shifted to the left by f of c. It is essentially that impulse. Remember, direct delta is a impulse function, except here that impulse is located at f of c. But that shouldn't be a surprise, because our signal has only one frequency component, f of c. So what this exercise has told us is that when I do this analysis, remember Fourier transformation, this particular equation, we have called it as an analysis operation. When x of t is just a single complex exponential rotating at fc hertz, and if I do the analysis part is going to tell me that my signal has only one frequency present, and that is evident from this answer. In the frequency domain, all the values of f are 0 except the value at f of c, and there I have this impulse. As soon as I move away even slightly from fc in the frequency domain, I get nothing. Obviously, because x of t doesn't have any other frequency apart from f of c. So the Fourier transformation of this complex phasor is very intuitive. It is the outcome of our analysis that we have done. What if this x of t is multiplied by some scalar? Let us say instead of having a unity voltage magnitude, we have x of t which is scaled by some scalar a, and this a, by the way, can be real valued, or we do not prevent it to become complex valued either. Essentially, it is scaled by some scalar small a. If you repeat the derivation, we get the same answer of this delta function centered at f of c, except now you see that the delta function has been weighted by this small a. Why? Because the input is weighted by a. So our analysis is correctly telling us that there is only one frequency present, that is why it is this delta function, and that frequency is additionally weighted by this scalar a. Okay, now let us consider a slightly more complicated signal, which is not just one exponential, but it is actually a sinusoidal function with amplitude a and frequency of f of c. So x of t is a times sine of 2 pi f of ct. This is something very practical. Sinusoidal signals, as we have remarked earlier, they are present everywhere. All the electromagnetic signals ultimately boil down to these sinusoidal waves. Now, you may have seen from your high school math that this sine function can be written as summation of two complex exponential functions, one at f of c, another at minus f of c. And this a further gets scaled by 1 over 2j. So this is the expression for x of t. And so now I just apply the observation that I got from example 2, and I right away conclude that the Fourier transform of this signal must be given by this expression. So what this expression tells me is that this sine has two frequency components, one at f of c, other at minus f of c. This is one is at f of c, this is minus f of c, and they are getting weighted by this complex scalar. If I look at this signal x of t in time domain, I have waves. I think of a wave. It is an oscillating wave which goes from minus infinity in time to plus infinity in time. But if I change my viewpoint, and instead of time domain, if I transform over to the frequency domain, I just get two impulses. One located at f of c, other located at minus f of c. And the height, the weight of the impulse is given as a over 2, a divided by 2. So this is the Fourier transformation of the sinusoidal signal. Now, typically x of f is going to be a complex number. That is what we saw on the previous slide, that there was actually a divided by 2 of j, where j is a complex number, it's an imaginary number. So whenever we are dealing with complex numbers, we can't just simply plot a complex number in a two-dimensional plot the way I have done here. What we would need to do to specify the complex number properly is to show what the magnitude looks like and what the phase looks like. What I have shown here is just the magnitude aspect. Actually, I would need to specify the phase of this Fourier transform also to completely specify the Fourier transform x of f. I haven't done it here, but I leave it as an exercise to you to determine what the phase should look like for this particular example. Now, if we look at example 3, we went from time domain to frequency domain, and we also can see that by inverse Fourier transform, if I am given this type of frequency domain, what is known as spectrum, then I can recover my time domain sinusoidal signal using inverse Fourier transform, using the synthesis operation. Basically, I would generate a complex exponential at f of c. I would generate another complex exponential at minus f of c. I will give a weight of a divided by 2 divided by j to both of them, and then I will subtract this from this, and so basically I will get this signal here, which is nothing but my time domain signal. Essentially, I did inverse Fourier transformation. I did synthesis of my time domain signal given the information contained in the Fourier transform. And so that is why we have two different viewpoints, and this is kind of represented in this following manner. If I'm looking at if I'm looking at this signal from time perspective, the signal looks like this, the red colored oscillating wave. But if I change my viewpoint and if I go to frequency domain, the signal looks like this, just two impulses, one at fc, other at minus fc. There is additionally a phase component to the frequency domain which we are not showing here, but this is how it looks like, at least in the terms of magnitude component. Now you may ask, but what is the real signal? The answer is either one. You can call this or this. Both are same. They both are the same signal. The signal itself doesn't say that I just have only time domain representation. The signal also doesn't say that I have only frequency domain representation. The signal is a signal, it's a physical entity. Typically, we are used to seeing the signal in a time domain perspective, but actually the same signal can also be represented in its entirety, in its all completeness, from a frequency domain perspective also. You might ask that, but no, that cannot be the case. I mean, the sinusoidal wave looks like this only. How can it look like this? Well, I mean, who knows what it really looks like, right? When we look at, for example, light, I mean, we know that light is a wave, which, apart from this wave-particle duality of quantum physics, we know that light is a wave, and so that wave has this oscillatory nature, which is shown here. But we haven't seen this oscillatory nature ourselves. It is equally correct to say that the light in the frequency domain is like this. In fact, there is in fact a reason to say that for our brains, the light looks like this, in fact. Why is that? Because uh, our brains are able to detect different colors. And the way they may be doing that is by taking Fourier transformation and looking at which frequency is present in the light. Different colors have different frequencies. And so if a particular color arrives, our light detects it as an impulse somewhere over here. If a new color arrives, maybe that impulse shifts. And so suddenly we feel that we are looking at a different color. And so maybe our perception mechanisms have this Fourier transformation inbuilt into them. We don't know. Anyways, the point is that both of these are completely equivalent ways of representing a signal. The signal remains the same, whether you can look at it from time domain or from the frequency domain. To go from here to here, you apply Fourier transformation, and to go from frequency domain back to time domain, you apply inverse Fourier transformation, which is indicated by f of inverse. Okay, now there is one more thing that is quite interesting that we should consider, but let us stop here for the time being and we'll come back to it in the next lecture.